Welcome to all. In this presentation, I discuss the quantum computing technology. The today talk is discussion about the investigation of the quantum computing phenomena in a great details in a developing area of information science. I am Dr. Neeraj Kumar Mishra. I am the Associate Professor at Vellore Institute of Technology, AP Campus, Amravati. Today, Ira, on one of the main challenge in the digital logic circuit, the problem is the power dissipation. In this way, many ICs are there to control all the control the uh, inputs and process and give the provide output. So IC has a more number of application, maybe in computer or maybe in aeroplane or maybe in healthcare or maybe in the camera or in the IoT, in the Internet of Thing or in any communication device. We come to the lower node, technology node. The problem is lots of the problem faced in the computing system. The main challenge is the device length, and further reducing the device length means the device performance is not very better. So we need some alternative technology to find the best solution. Okay, so in this way the computing is beyond CMOS. So mostly nowadays there is a new emerging domain come in this era, maybe your quantum computing or neuromorphic technology or approximate computings. So all these technology is based on the beyond CMOS computing. Okay, so the emerging domain is like a reversible computing, neuromorphic, spintonics, and reconfigurable molecular quantum cellular automata. Okay, so that what is the quantum revolutions here? So many of the big institutes or many of the research institutes are focusing on the new computing device to develop emerging devices. So recently, the Google has developed 72 qubit quantum computing device, and IBM also developed 53 qubit quantum computer device. So the future goal or future scope is the IBM promise 1000 quantum computing device to process the more number of qubits. So these are the classical gates like AND, NAND, XOR, but all these gates consumes a more power dissipation because here information is erased during the computation process. Okay, so reversible logic is one of is the phenomena in which there is no information loss and the circuit is has a very low power consumptions. So in accordance with the Bennett theorem, they discuss the one bit of information erased gives a thermal energy that is KTLN2 joule. But Bennett has proved that energy consumption to be theoretically zero if we go for the reversible computing. Okay, so in reversible computing, the energy loss is zero, but if we go for irreversible computing, the energy loss is give more than KTLN2. So if the number of bits are more, the energy dissipation is also more. But in reversible computing, there is no information erase, so there is no energy loss. Okay, so now all the quantum computing device, the information processing bits is qubit. So all the qubit is superimposed by use the concept of superposition theorem. Suppose that 0 qubit is associated with alpha and 1 qubit is associated with beta. That means both the qubit is superimposed by superposition law. Okay, and the magnitude of alpha and beta is always 1. Okay, so the qubit is actually used to measure the information in a quantum computing domain. Okay, so reversible computing is the part of quantum computing because reversible gates are used for the quantum circuits. So in reversible computing, there is a certain phenomena or certain characteristics. One thing is that equal number of input and output, and the fan out feedback path and loop is not allowed in the reversible computing. Otherwise, the reversibility property is lost, and the circuit or the design is not reversible, and the energy is dissipated because information is lost. Okay, and reversible computing, the number of input and output is equal, and also the unique mapping between input and output. Okay, so irreversible computing is only compute in the forward direction, but reversible computing or reversible circuits go in the both forward and backward direction for uh, computing the output and also recovering the informations. Okay, so another things is in the quantum computing domain, the main phenomena or main parameter is a quantum cost. So quantum cost is measured by the number of 1 cross 1 or 2 cross 2 gates such as C naught gate, CV gate, CV plus gate and NOT gates. So these gates are involved in the quantum circuits, and if we count the number of primitive gates in the quantum circuits, so that number of gate represent the quantum cost. Okay, so other parameters. So what is the motivation of reversible logic? Reversible logic is a ultra low power nanocircuits, and they here no energy dissipation. That means the performance beyond sub kT kT limit. And here the recovery concept, that means no information is erased and the power consumption is very less. So the application of nanotechnology may be optical computing, quantum cellular automata computing. Okay, so in classical circuits or quantum circuits. So what is the difference between classical circuits and quantum circuits? So classical circuit is only use bits. Bits means logic 0 or logic 1. But in the quantum circuits, the information is qubits. And classical circuits, we are using a classical gates like AND or NOT or universal gate NAND and NOR. But in quantum circuits, the gates are quantum gates, not a classical gate. And classical circuits are irreversible, but quantum circuits are reversible. And all the classical circuits are implemented by the CMOS level for reducing the power consumptions. But there is a certain limit due to the limitation of scaling. But in quantum circuits are implemented by the superconducting technology. Okay, so now we come to the some basic quantum gates like Paris gate. So this is 3 cross 3 gate, means 3 input and 3 output. So the quantum cost is measured by the counting of primitive gates like CV gate, CV plus gate, NOT gate, or C naught gate. So here the counting of gates, if we count the number of gates, we get 4. The quantum cost of Paris gate is 4. Now some other 2 qubits gate is also there like swap gate. Swap gate is like a Fredkin gate, and C naught gate is like a Femin gate. Okay, and what are the programming tools are there? So one tool, many tools are there like QuizKit that is developed by IBM, and PyQuil that is developed by Google, and Project Q, and RCViewer and RaveKit. So these are the representation of the qubits in the matrix form. Okay, so one qubit gate is known as a Hadamard gate, polygate, polyx, poly-Y, poly-Z, phase, or pi by 8 gate. And two qubit gate is known as a controlled NOT swap gate. Okay, so two qubit gates means how to represent 0 qubit in the matrix form, and 0 1 is represented in the matrix form, and 1 0 is also represented in the matrix form, and 1 1 is also represented in the matrix form. So this slides give the overview how to represent the two qubit in the matrix form. So this is a matrix for Hadamard gate, and if we multiply the conjugate of Hadamard gate, we get a matrix. So this is the matrix we are presented here. Okay, if two Hadamard gates are joined together, that means we get a identity matrix. Okay, so this is the Femin gate, that is CNOT gate, and this is 2 cross 2 gate, and this is the matrix representation of a CNOT gate. So these are the basic quantum gates are used for the implementation of any circuits. Maybe polygate, poly-Y, poly-Z, Hadamard, phase, control NOT, control Z, swap, and Toffoli gates. So here this is an implementation of the quantum gates in the IBM Composer. So we know the CNOT gate, the dot point represent the control point, and the one another point is a control is the qubit. Okay, if the control point is high, then the qubit value is changed. Otherwise, qubit is unchanged. So here we measure here if we measure the output, we get a probability. Okay, so here we get a probability of in what is the probability? So probability is 1 0. Okay, so here many gates are implemented. Okay, so now what is the quantum computer? This is a look of quantum computer. So that is developed by IBM. Okay, and the cloud access is given by the IBM to many person. That is open access. Okay, and some quantum libraries like square root of naught. So different values of qubits may be 0, 1, V, and V plus. Okay, so these are the CNOT gate, 2 qubit gate, 2 cross 2 gates, and this is the tool for designing of quantum circuit, that is RaveKit 1.3 version. Okay, so another thing is that what is the library of quantum circuits? So there is a 4 libraries of quantum circuit. The first library is NCT. So NCT represent the NOT, CNOT, and Toffoli gates, and NCTF SF represent NOT, CNOT, Toffoli, swap, and Fredkin gate, and GT represent multiple control Toffoli gate, and GT and GF represent multiply controlled Toffoli and Fredkin gate. So all these gate is actually used to process the input information in a very fast way. So nowadays, if you look at the situation of COVID, that means this molecule is very much complex, and the complex system processing means more powerful. Then then the molecular computation process to be fast by only the quantum technology. So this is like a supercomputing device, computing system. based on quantum computing. So quantum computing is very helpful to analyze the complex system or complex molecules in a fractional of time. So that's why this is a more advanced topic. Okay, so this is the quantum gates, and here the reversible and quantum circuits are shown here. So what is the implementation part of quantum circuits? Some implementation part is based on the quantum dots, like maybe molecular device or ion trap technology or spintronics technology or maybe other emerging quantum technology. Okay, so now I will just say that the quantum technology is very helpful for all the emerging field, maybe optical computing, nano computings, and fast processing of informations, maybe uh, supercomputing systems. So this is all about the quantum computing. Okay. So in this presentation, we have discussed about the quantum gates and circuits, and we discussed the library files of quantum circuits, and then we have also discussed the number, the reversible gates, maybe 1 qubit or 2 qubit or more than 2 qubit, and we learn the quantum cost, how to measure the quantum cost, and what are the emerging technology to implement a physical, real or quantum devices, maybe spintonics, molecular quantum dots, or ion trap technology, and many other things. Okay, so thank you for all to listen this presentation.